Welcome everybody in the lecture hall. Welcome everybody on Zoom. Welcome everybody watching us from the future. So today we are going to continue our exploration of these other data shapes. So remember that the high-level take-home message for the entire course is that data has shapes: trees, tables, graphs, cubes, vectors. And the shape is probably the most important decision factor in the system that you're going to use, because everything follows from that. The syntax, the logical model, the validation, the query language, how you process it, how you implement it, and so on. So we spent most of the semester discussing tables and trees. So the tables you knew from the bachelor's relational database lectures, and we saw that trees are denormalized tables. And so now we are looking at graphs, and next week we are going to look at cubes. So where were we? Well, I explained that the logical model is the labeled property graph, right? It's basically a graph made of nodes and edges, directed graph. The nodes and the edges can have properties. The properties that a node or that an edge has is basically a flat JSON object. You're just allowed to also have lists of strings, lists of integers, so homogeneous flat lists inside, but apart from that, it's just a flat JSON object. And we saw that the nodes can have labels, multiple labels, and that the edges can also have one label on every edge. So that's the logical model. Then we saw that there is a query language called Cypher that was the query language introduced by the Neo4j framework, that is a graph database system. And I'm introducing you to this query language. So last time we saw all of that. We saw that it's actually, because it's JSON objects in the properties, the language actually supports something that looks a bit like JSON, right? It's not exactly JSON, as you can see. There's a few differences, but more or less it's only a documentation lookup away, the details of that, right? So just remember that you can use something a bit similar to JSON and JSONic in the way that you build your objects, including the navigation. Again, it's one documentation lookup away. I wrote a message to the Moodle forum yesterday, for standardization. You really need for this lecture to focus on the high-level patterns that there are in the languages and so on. The details, if we start counting with 0 or 1, if there's 2 square brackets, 1 square bracket, if there's quotes, if there's no quotes, it's really just a detail, right? So this is not what your focus should be on. It's the high-level patterns. So this is very similar to JSONic navigation. This is very similar to JSON and JSONic. Now I'm going to go to clauses. This is where I left you last time, with the idea that we have something similar to flower expressions. I would say it's more similar to flower expressions than to select from where, because the clauses are also flexible, just like in flower expressions, the W3C standard. So this is why I would like to think of that more like a flower expression. Actually, it's even more flexible because unlike JSONic and XQuery, the return clause on its own is totally fine. Just say return blah, 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 and then you get that result. Actually, it would be the same in JSONic. If you don't have return, you just return this, right? All right. Then we have the with clause that can come as one of the many clauses you can have in these flower-like expressions. So here you have whatever you're writing in there, like some expression, and then you bind it to some variable, right? So if you see that as some sort of data frame where every variable is a column, then list would be one of the columns of the data frame. So basically, the way you can visualize it with the semantics of flower is that after the with clause, you have something that pretty much looks like a data frame with a column called list. And then you have, for every record, what is created by the clause. In fact, here it's only one because you only create one single value. So it's going to be a data frame with one column list and one value, which is this. And then you evaluate this for the only value that you created, list 3 bar, and that's pretty much equivalent to the previous slide. Who is still with me? Right? Very good. Okay. So now, I told you the with clause is similar to the let clause, right? In JSONic, you would say let $a equals, colon equals 1, return $a plus 1. Here you say with 1 as a, return a plus 1. There is a bit of a subtlety, though. There is a bit of a subtlety because you can pipeline them, right? So in JSONic, you can do that too. Let $A equals 1, let $B colon equals $A plus 1, returns $B plus 2. So here, there's no difference with JSONic. But here's the difference. This is not allowed. What are we doing here? You can see we are trying to reference, I don't know what's happening with the light, that the reference here references a previous with clause that was in the past. It's not the last one, the last with clause, but it's the one before. In Cypher, you can't do that. In JSONic, it would be allowed. In Cypher, you can't. You can only reference the last with clause. So the way you would do this is slightly different. You need to repeat in the second with clause, you need to repeat the previous one so that it's also part. So now you have A and you have B. Since you don't assign anything to A, it's just implicitly taking it over from the previous one. And now you have, again, A and B accessible, and you can do this. So you should visualize this as here. That's basically something like that looks like a data frame with a colon A and one record set to 1. What you have here would be the tuple stream here would be a data frame with 2 columns A and B. And then you have the record, in that case, 1, 2, right? Who agrees? Right? And then you return A, and that returns just the value 1. So you see, there are subtleties like that, but you can still more or less map it to JSONic as long as you're aware of the small subtleties that they are. So here you just need to repeat. In every with clause, you need to repeat all of the variables you still need so that you don't hide them, so that you don't lose them. You can also do this if you refer to both A and B. Again, that's because the last with clause has them both, right? Yes, there is a question over there. We don't have a microphone, unfortunately, so just... Tuple
with 1 and 2, or is it just assigned the value?
It's assigned the value 2. So you really have, so the tuple would have 2 variables, A and B. A would be bound to 1, and B would be bound to 2 because that came from A plus 1, from the previous, right? So I'm saying variables. I'm not sure Cypher would call A and B variables. They might still call them attributes or whatever. But if you connect it to JSONic, then that would be $A, $B in JSONic, right? So the way to read this A plus 1 as B, and maybe that was the sense of your question, is that you need to mentally cut it here. You have on the left A, and on the right A plus 1 as B, and not like this. Right, if that was your confusion, right? So we really have A and we have B that is A plus 1. Everything good? So then we have other clauses. Don't be scared, these are new names, but it's totally familiar territory. Because this unwind clause is actually the same as a for clause in JSONic that just explodes an array. Remember the lateral views, the explode function in Spark SQL, the for clause. So in JSONic, we would basically have for $B in $A, that would be the equivalent of unwind A as B. Everybody with me? Right? So what happens is that it's basically let $A equals this horrible thing, and then for $B in $A. So now you create, you have multiple tuples, and then you return $B. So here you need to imagine something that looks like a data frame with 1 column called A and 1 record that has this value. After unwind, you will have a data frame with 1 column, again, because you forget A, right? So you have unwind A as B. And now you have how many rows in that data frame-like structure? 3, exactly, because unwind, I never know unwind. Is there a native speaker of American? Help? Unwind, yes? Unwind, okay, so I'll say unwind, thank you very much. So unwind A as B makes it 3 records, and that is going to return 3 objects in that case. 3 maps, sorry, we call them maps in the data model of Cypher. Okay. Then I can also combine the clauses. It's just like JSONic. In any order, I can have with, unwind, and then again with, and then return. So you see what's happening here. I had my 3 rows in this data frame-like tuple stream structure. And then what I do is that I create now another tuple stream with just C as the variable, obtained from B plus foo plus 1. Who can tell me the contents of the tuple stream that we have after the second with clause? How many Columns, how many records? Yes? Exactly, 1 column and 3 records. What are the values of these 3 records? 2, 3, 4, exactly. That's b.foo plus 1, b.foo plus 1, b.foo plus 1. You see the similarity with JSONic, right? Having gone through the effort of learning JSONic, now it makes it much easier to learn other languages because the high-level structure is very similar. And then we wrap C in an array. So we are going to have now an array with an array with 2, an array with 3, and an array with 4, right? So 3 arrays. Okay? Where clause? We already know that too. That's just like the JSONic where clause. It's just going to filter. So now it's only returning how many tuples, the where clause. It has 3 incoming tuples. How many outgoing tuples from that clause? How many survive? Yes, 2. We have basically 3 and 4. Do you agree? 2 is not going to pass that bar. 2 is not greater than or equal to 3. So now we are going to have 3 outputs, an array with 1 value 3, an array with 1 value 4. Okay, so that's the idea. There's many, many other clauses. I'll come back to that match in particular, because we are creating graphs, because right now it doesn't look like graphs, right? So you're going to tell me, why is that a graph language, right? But here's the thing, this is coming now, the graphs. Is there a question over there? Oh, that wasn't a raised hand, okay. Who has ever seen ASCII art? We are going to do some ASCII art. This is exactly how the Sapphire language is built. Here's how. I have on the left some labeled property graph. It's just that I labeled the nodes with colors, and I labeled the edges with dash, not dash, right? But you have to think of them as labels. In that particular example, there's only 1 label per node, but there could be more labels, of course. So on the left, you have the database. Imagine it could be billions of nodes like that and edges, right? So that's the database as it is stored in our database system, right? How? We don't care. It's just stored like this, and we have this as the logical database view. On the right, this is a query. It doesn't look like it because I didn't turn that into ASCII art yet, but I will do that very soon. And our query says, I'm looking for some node followed by an edge that is dashed. So it has the label that corresponds to the dashed line, leading to a node, leading again via an edge that is continuous. So it has a different label that is continuous, leading to that node. Can you spot a few results on the graph in your mind? Yes, you can, right? So you're looking for example, that's a dashed line followed by this. So this here, these 3 nodes connected like this are a query result. There's others. For example, this one is also a query result, right? This one is also a query result. This one too, I don't know if I put it too. Okay, yeah, that's a query result. So the sort of queries we have is that we're looking for patterns. I have a query that is a pattern, and I'm looking for everywhere in the graph where there are patterns like this. So now I'm going to slowly, because I need ASCII art, and I don't know how to do dashed lines in ASCII art, so I'm going to give them actual names, right? So the dashed line will say that's label A, and the continuous line that's label B, right? I'm just giving them names as they have actually in the labeled property graph. This is the ASCII art. So the ASCII art, look at this. We have the first node, we give it a name. It can be any name. So let's call them alpha, beta, gamma, but it doesn't really matter. So I have alpha, and again, ASCII art. So there's an arrow here that goes from alpha to beta, and an arrow that goes from beta to gamma. And inside the arrow, you have to have a bit of imagination. There's the label of the edge. There's a colon. What's after the colon is the label. So colon A means we're looking for an edge that has the label A. And here we are looking for an edge that has the label B, right? In fact, it's exactly the same thing as this. If I consider dashed is A and continuous is B. Who sees that? It's the same. So this is in fact Cypher. This is my query pattern. And this is one possible result. And again, there's all the results I've shown you, right? So far, so good. So now I gave the labels, I named the labels to the edges. Let me also give labels to the nodes, right? Let's say the yellow is actually yellow, the string yellow, and the label yellow, and blue is BLUE, right? So the label blue. So I can slightly modify my ASCII art pattern to say that beta here that used not to have any constraint, now I'm putting a constraint. I'm adding a colon. And again, it's the same rule as here. What's after the colon is the label. So here it's the label of a node. Here it's the label of an edge. So I have beta colon yellow, right? Again, beta is just a variable name. That's how I call it. It's going to match. When I match the pattern, beta will be attached to the middle node. But it has to have the color yellow. So that's going to return less results because the results, for example, this one, if I can operate, yes, this one right here will not be in the results anymore because this is blue, right? But this one will be in the results. We still with me, right? Then we have, what about properties? Because so far we only restricted on labels. So if we want to restrict on a property, I can also add that in my variable, but before the colon, right? So here there's no colon in name Einstein because I didn't restrict on a label, but there could be a colon together with it. So we say alpha name Einstein, that's going to specifically filter those nodes whose property name is equal to Einstein, right? So this is a specific filter. So you see in my ASCII art pattern, I can filter for specific labels for nodes and edges and specific properties for nodes and edges. Here's an example with both a label and a property, which actually reminds me, because that wasn't on the top of my head, the property is actually after the label, not the other way around. So we have here gamma, the third node, that must have the label blue, and that must have the property name equal to ETH. Okay, so now I have two filterings on the third variable. It must both have a specific label, and it must have some property specifically equal to ETH. Okay, so that's basically how the query patterns work. And now, because it's ASCII art, you can also have arrows in the opposite direction, right? You can have more complex patterns. So here we're looking for alpha pointing to beta, pointing to gamma, and delta pointing to gamma, right? With the labels A, B, and B, right? All right, and you see it matches. You see here, if this is alpha, this is beta, this is gamma, this is delta, you see that this arrow here goes from delta to gamma, as expected in here, so this all works, right? So this you can do this in your query pattern, and you can even continue, right? You can even have a loop like this and have alpha twice. Now you have an undirected loop in here, right? You see that delta goes to alpha with the label B. Who is still with me? Not lost? Okay, so it's very, very intuitive. And then we have plenty of bells and whistles. I'm not going to drive you through them all, but you can look at the documentation. For example, I can say between alpha and beta, I want a path, not just a single edge. I want a path of length between 1 and 4 included. It can be length 1, length 2, length 3, length 4. And this here qualifies. 1, 2, 3, 4, that's alpha, that's beta, that's called anchoring. So this is anchored to beta, anchored to alpha. And this is going to be done for all the matches, right? It could be that you find 100 different matches like this. This is just one particular example, right? So you can do this. And when you have like this, some pattern that you want to match against a graph, you can put it in a match clause like this. So now you have match, followed by this beautiful ASCII art. This match clause is like any other clause going to generate a tuple stream, which you can, yes, let's go to the question.
What does the query return? Just alpha or all nodes in the path?
In that case, so let me explain the match clause, and I think that should answer your question that you have here. Because it's always in a match clause, right? This is not a query by itself, that's not a query alone. It's only a query if you put it in a match clause and then return something. So in that, let's look at that query. It's a pattern that has 3 variables, alpha, beta, gamma, and some specific filtering on a property here, a label here on an edge, and a label on an edge. If now you visualize the tuple stream that comes out of that match clause as something that looks like a data frame mentally, can anybody tell me how many columns that data frame-like tuple stream would have? How many columns? 3? Yes, that's absolutely correct. We have a colon for alpha, we have a colon for beta, and we have a colon for gamma. How many records? As many as matches, right? So for every match, we are going to have a record. So we could have a data frame with 3 columns and let's say 100 records for all the matches. Now, you have also to see that the types of the values in there previously, when I showed you this query before this, when I showed you this, the types of values we had in our tuple stream were maps, arrays, integers, and so on. Can anybody tell me the types of alpha, beta, and gamma that we would have then in that data frame-like structure? What types would they have? Yes? There's node types. There are node types, absolutely. And you might remember, and now maybe you're starting to connect all the slides that I've shown you, and I'm just going back, so just maybe ignore while I go back. Yeah, you see, node here is a perfectly fine type in my Cypher language. So it's just going to be alpha, beta, gamma will have values of that type. They are nodes, right? Logically. Internally, there might be memory pointers or ID or whatever, but here we're on top of a query language. So we don't have to care about the physical implementations. It's just nodes. Alpha is a node, beta is a node, gamma is a node. And you'll see we could have also relationships and paths in more elaborate queries. So now I'm coming back. Just close your eyes while I'm doing that. Yes, okay. So everybody with me? Okay, so 3 columns, alpha, beta, gamma. Is there a question? Yeah? I think it's a Turing-complete language, so probably whatever you want to do, you'll figure out a way of doing that. It might be, though, that you need multiple clauses, because the match clause, as you can see, somehow it's linear, right? ASCII art is well, technically ASCII art can be 2D, right? But here it's 1D ASCII art, so you might not be able to do everything you want, but then you can use multiple clauses and find a way to build a query that does that, right? That's actually a good question. We should check if the match clause is more elaborate than just a single undirectly connected pattern. I'll take a look at that. Can we make a note? Yeah, I'll get back to you. I'll look at it. Yeah.
Query for triangles,
Mm-hmm.
which I think you can.
Mm-hmm. Yeah.
And it's already like a quadratic complexity to look up the triangles in the graph, right?
Yeah.
And it increases.
Mm-hmm. Yeah. So here you're talking about the physical implementation already, right? Which is a very good thinking. You have to think about these things. So here, the 2 words that are very important are data independence, right? So we have a query language that declaratively says what we want to obtain. So it tells you, okay, the results are going to be this and that. And then you implement it, right? So I will not go so much into the details of the implementation here, maybe the storage. But what you need to keep in mind if you want to understand the physical implementation, they are actually indices. So we can build an index, for example, here on the property name. So we can build an index that indexes the nodes on that property. And then we just look up Einstein in that index that will directly give you the nodes that have the name Einstein, which might be very little, and then the rest is just a bit of post-processing in memory, right? So there's very advanced ways to actually make that very fast using plenty of indices in the background that accelerates the lookup. So part of them will be very fast through indexing, and some others will be some filtering in the memory, right? It's a good combination, right? But that's the power of data independence, because we specify the language and the logical model, and then anybody is free to implement it in any way they want, using indices, using all kinds of structures. Does that answer your question? Yeah, awesome. Over there, yes? Mm-hmm. That's basically what I wanted to look up, because since it's 1D, technically you can only have some sort of undirected line, right, of nodes in this way. If you want something more complex, I think I will try to find an example offline, but I think it should be possible just using more clauses. Once you have bounds to a specific pattern, you probably can have more clauses that are going to attach to more patterns. right? I'll research that. That's a good question. Right. My intuition is that the language should be powerful enough to allow you to do these things. Yes?
Can we match relationships instead of nodes?
I think you can. That I will also confirm, because if you look, I mean, naively, if I look at this, it feels like I should also be able to put a variable here, right? So we'll check also that and tell you. The reason why I have this intuition is that in the type system, you also have relationships, right? So it could make sense that you can also do that. I just don't know from the top of my mind, right?
So it's more just alpha, beta, gamma.
It returns a colon for every variable that you use, right? So in that case, you just have explicitly alpha, beta, gamma, and that's why you get 3 columns. But if you add the delta, epsilon, and so on, then you will have more columns, right? You decide. When you put your pattern, you are the ones who say the variable names, and that's going to create a binding for every one of these, right? Thank you. Yes?
Is it allowed to which features, example, all the next class between Zurich and Berlin?
All the possible. Flights between Berlin and Zurich. You mean the general how this generalizes, right? So there's more than that. Here I'm just showing an example. There's a lot of bells and whistles in what you can do, right? It's very powerful. So maybe if you have a specific example in mind, I can also come back to you offline. Right? Okay. Are you taking all the notes of what I have to do offline? Because I took a few homework here. Yeah, go ahead. I think it has to be in this order because return is the last one. Right? It's just like in flower expressions. You have plenty of clauses that generate these tuple streams. But once you reach the return clause, you no longer have a tuple stream. Now you have the results, the actual results. So the return clause has to be the last clause. Right? Does it make sense? Oh, you mean with a line? Do you have to have a new line, right? Is it your question on the same line? Yeah. Yeah. Oh, then you could say maybe you can use gamma, alpha, and beta and write a more complex expression in the return clause that does something more complex, right? Here we just return gamma, but the return clause can take more complex expressions. Yeah, so you could add more things in there. Right? Was that your question? Yeah, all right, awesome. More questions? And on Zoom, did that answer your question, what I explained on the match clause? Yes, it did? Okay, awesome. Yeah. I'm less of a specialist of Cypher, so this is why I have to look up some things offline on this. I have less experience. All right. Then, of course, you can combine because, as I said, it's like in JSONic flower expressions. You can have the clauses in any order you want. So match, where, return, and so on. Here you have match with where, you see. So that's also combining. So you see here, if you look at the details, how many columns do we have in the first tuple stream after the match clause? How many columns in this data frame-like structure? Do it with your hands. 2, exactly. So there's George and other person. And here with we create 2 columns, other person and uppercase name. Here we filter on uppercase name, and then we specifically return the other person name, right? So this is another example of chaining the clauses in a way that is more general than SQL. So you see this idea of having plenty of clauses that return tuple streams that can be put in any order with a return clause at the end. It's not just for trees. It's not just for JSONic or XQuery. It's really some very, very general idea. Even in SQL with the pipe syntax in BigQuery with Google, they are doing that now. So this is really a very high-level pattern that is the same across all of the shapes, right? So it's very convenient. And again, here I made you a slide where it explicits the actual tuple streams. The tuple streams are just the bindings, right? So here you have a binding of this is bound to George and this is bound to other person with 2 bindings here. Tuple streams is the W3C standard name because technically W3C calls this a tuple and this a tuple, and then you have a stream of tuples. and every clause produces a stream of tuples that it feeds into the next clause that produces another tuple stream, feeds in the next clause, and finally at the end you have the results. And again, the tuple streams can be visualized as things that look like data frames, because that's something you can actually parallelize quite well on systems. Okay. You also have updates. That's good because it's this convergence of transactional and analytical that is ongoing. So you can also create nodes. That's like an insert statement in SQL. So here we just say create this. That's going to just add these things to the graph. Here it creates a node called Einstein, a node called ETH, and then it connects them via an edge that has the label visited, right? And it puts some properties. Who understands that query? Right? So it's going to modify the database by adding these two nodes. Now, it might be they already exist, but create doesn't care. It's still going to create them. If you want to not recreate stuff that already exists, if there's already Einstein in the database or ETH, then you use merge instead of create, right? And if you use merge, it will look if it already exists, and if it already exists, it's not going to create new nodes. I should put a star with merge because merge is non-standard. I will talk about the standard later. This is standard. Merge is not standard. That is Neo4j specific with the Cypher language. So there you go. You have plenty of clauses, even more than in JSONic actually. Unwind, create, remove, merge with, delete, limit, order by, skip, for each, set, union, and so on, right? So you can probably guess what some of them do. Order by, you can probably guess. Skip, you can probably guess. Set in order to set a specific property, and so on, right? And again, the documentation is your friend, right? Then once you know the general principle of how the clauses work, you can just look up what you need and understand the clauses independently. So now you should have what you need to play around, right? Is everybody with me? Right? Who sees the similarity with the flower expressions? Right? Very good. That's exactly your thinking. Because when you see that, there's less to learn, right? Because it's exactly the same structure behind the scenes. Is there a question on Zoom? Yeah.
Why are there two unions? Is it like union all versus union in SQL?
Oh, just because I was drinking too much orange juice when I designed the slide. So there's no reason why I put it twice. Yeah. Okay. But thanks for asking. I mean, you never know. Okay. So now I wanted to tell you what's new, because this is actually quite recent and it took a while. They were faster than the trees, actually, because the trees, they still haven't standardized on something everybody agrees on. But the graphs, it's done. So there's two standards, actually. One of the two standards is on top of SQL. It's an extension of SQL that provides you with that extends it with the graph matching patterns. I'm not getting into this because that's a mix of SQL and what I've showed you. But the language I've showed you would be this other standard GQL. So this one is 2023. That was in 2023 that there's the SQL extension that supports graphs. So basically it supports both tables and graphs. GQL is the standardization of Cypher, kind of. So they talked with different database vendors and they gathered and they had a lot of meetings and they finally converged. And it turns out that the Cypher language I've shown you is very, very, very close to what became the GQL standard. Yeah.
But is there also something like set/bag union?
Sets union, I didn't get that. Set bag union. That I can also look up offline. That would be like union all in SQL, right? Is that what you have in mind? Union and union all? Yeah, that I can also tell you. I can tell you that there is a return distinct. So if you just say return, you might have multiple nodes if they are matched multiple times. But if you say return distinct, then it can eliminate duplicates. It might be that union has something like this, and that I can also investigate. That's a good question to ask. Yeah. All right, so the SQL extension with graph support, I'm not showing that to you, right? And this is pretty much the standardization of what I've just shown to you. So it dates back to 24. It was just last year. On the history timeline, it's actually already far away in the past, but actually not so far away in the past. And now you see what's going on, and that's basically who read the Moodle forum message that I sent yesterday on standards. Yeah. So now something that's happening is actually typical, is that now that GQL was successfully standardized, Neo4j made an announcement that they are going to start aligning Cypher with GQL. So they have in the documentation, there's a page, you can look for it, that has exactly what Cypher already implements, the mandatory GQL features, the optional GQL features. Then you have a list of the Cypher-specific things that are not in the standard, like the merge clause. And then there is a list of all the features of GQL that are not yet in Cypher, right? So it's all documented, and you can expect that in the coming years, it's going to get closer and closer and closer with the GQL standard. That's excellent news because it means that if you learn that language, you can expect that a lot of other labeled property graph database systems will also support that standard. So that's excellent news for the database community that it went that far. It took years, a lot of efforts, but it was worth it because now we have that. Okay. Now a few words about the architecture of Neo4j. Very quickly, I'm going, of course, I don't have 4 weeks to go over that, so just very briefly. The idea is that you replicate data in a similar way that it's done in MongoDB. You basically have a server that has the entire database, all of the nodes and edges and properties and labels are in here, and then you replicate here, you replicate here, you replicate here. It's just like one replica set in MongoDB, right? So that is the early versions were doing that, right? There's just one, it's not partitioned, it's not sharded or spread across machines, it's only replicated across machines. So at first it seems like a limitation because it means that the graph cannot be larger than what fits on a machine, right? And so of course, the researchers in the graph database community, they started thinking, how do we shard a graph over multiple machines? How do we do that? They are also doing that for the blockchain. For example, Ethereum and so on, at some point started sharding also over multiple machines. It's a very difficult problem, right? And at some point they had, so let's put it this way, they found a solution at Oracle. Oracle has, their graph database is called pgx.d. They also had their own query language, but again, since now we have the standard, they are also going to converge to the standard. I think their language was called PGQL or something like that. But again, now they will converge to the standard. But the interesting thing about Oracle PGX database is that they managed to solve the sharding problem in the sense that they can spread the graphs over multiple databases, literally. So you basically have to imagine that you have a first machine that has part of the graph right here, and then that node right here will have a copy or a proxy on the 2 machines, and then it continues on the other machine. This is essentially the way that they do that. So they manage to shard the graph structure, and they call that PGXD. D is for distributed, because they manage to put it across some machines, right? Spark, I think, also have, is it called GraphX or something? So there's also a Spark library that supports things like that, right? So now we know a bit more about that. On the side of Neo4j, they actually did not immediately do that. What they did instead is that they allowed the users to have federated databases. They basically said the user can have multiple of this. They can have a first database with people, another database with institutions, for example, and so on, with distinct replica sets, but it's actually completely distinct databases. And then they have what's called Fabric in the language that just allows you to give a name and to connect to all of these databases, and you federate them in the same query in the sense that in Cypher, you can say for that part of the query, the match that you have here should be on the first machine right here that has this database. I don't actually know in the example they have twice the same port, but it could also be different machines. And then you have this other database, right? And then you can, in the same query, it's here the union of the two, you can query some part on a database, some other part on a database, and then bring them together for your results, right? For whom is that clear? Right? But there is no partitioning here because that's not real partitioning. It's the user that creates multiple databases. It's not like we have a physical implementation that partitions. The burden is on the user and you have to configure in the way you see. However, just that year, they introduced something called InfiniGraph that does actual sharding of the labeled property graph. But a word of warning, what they actually shard is the properties and the labels. They do not shard the actual graph structure. So what happens is that on one machine, they have the graph structure with the nodes and edges. And the properties, which actually take a lot of space, they just outsource to other machines, and they even shard the properties across multiple machines. Since properties are JSON objects, it's probably natural how you can shard that, right? It's very similar techniques to what we saw with document stores and the way we process them in Spark, right? So it's a way forward. But still, again, the graph structure itself with nodes and edges is on the same machine. So that's called InfiniGraph. So you see there's motion, it's in motion, it's ongoing, and maybe at some point the Neo4j could also do it in the same way as PGXD. We'll see in the coming years if they also start sharding the graph structure. It's very complex to actually do that. Okay. Who is with me? Right? It's just high level, of course, the physical layer. Something also that I emphasize because this is the direction at the moment. You both have queries and updates. You both have a transactional and analytical, right? I'll talk about OLAP next week for the data cubes. This would be OLTP. You have a lot of updates, and this would be OLAP, where you have analytical queries, but now a lot of systems start doing hybrid approaches, which is called HTAP, right? Hybrid transactional analytical processing. So you'll see more and more of these, systems that are both capable of handling updates and of handling analytical queries. Okay, I have also a few slides about the internal storage. Actually, it's not very fancy, it's very low level. Of course, the graph structure itself, in the memory, you have this index-free adjacency. You just have pointers in memory. That was the whole point of having a graph database. On the disk, of course, you have to separate the ingredients, just like I showed you, right? On the disk, you store the nodes, you store the edges, and so on. But when you parse it into memory, then you reconstruct the graph. But what you also need to consider is that there's a bit more structure than just the graph, because there's the labels and the properties. And here again, it's pretty simple. It's simply linked lists and doubly linked lists, right? So here we have a linked list that has the labels associated with a node, simple linked list. So you just can go through that. And then when you have the edges that connects the nodes, you basically, it's two levels, right? You have the edges, but then you have the doubly linked lists that connect the edges, right? So it's a bit like you're driving a car through the graph, right? Or a train. So basically, once you're at that node and you have a query in your ASCII art thing that says, I'm looking for a blue edge, then you use the doubly linked list. Okay, what are all the edges that come and go from that node? Oh, here's a blue edge, so we are following it. And then again, it's like a roundabout, right? And then you select again with the doubly linked list the next edge you're going to follow. So who has the intuition how you can filter these ASCII art patterns in this way, right? You just stop at every node, take the roundabout with the doubly linked list and see the edges that you're going to take, right? And on disk, again, you have a node store, a relationship store, a property store, a label store. So you nicely store them like the cooking when you have the sugar, the flour, the chocolate, the butter, and so on, nicely separated. There's plenty of other products. So I gave you Neo4j, there's PGX, that's Oracle products, there's GraphX running on Spark, there is Turi, and so on. So there's plenty of other systems. And again, great news. GQL standard, so that's really awesome news because it's expected that they are going to, Apache Giraffe also, they are going to converge to this, right? RDF is for next week. That's the other community that I told you about. So I'll tell you about this next week, and I'll also look into data cubes. Thank you, Sarah, for moderating. Thank you for asking the nice questions and for the follow-ups. And enjoy the exercises. And don't hesitate to write us emails or on the forum if you have questions. See you next week on Tuesday.